Welcome back to Stellar Stories, where we discuss science, philosophy, and the mysteries of the universe. Today, we're tackling a mind-bending enigma that has baffled physicists for decades: the black hole information paradox. We're going to explore the concept, what it means, and why it's a paradox. We'll then be speculating about possible solutions to the paradox based on cutting-edge physics. So if you want to hear about baby universes, black hole firewalls, and quantum error correction, you're going to want to stay tuned. But before we move on, I'd very briefly like to say, this is a tiny channel, and every interaction from you helps immensely. So if you like what you see today, please consider liking and subscribing. The benefit of being a tiny channel is that I can respond to all of you. Now that said, let's begin. Now, before we get sucked into the abyss of this paradox, let's refresh our understanding of black holes themselves. These celestial behemoths are formed when massive stars collapse under their own gravity, creating a region of space-time where gravity is so strong that nothing, not even light, can escape. At the heart of a black hole lies the singularity, a point of infinite density where all matter is crushed into an inconceivably small space. Surrounding the singularity is the event horizon, the boundary beyond which escape from the black hole's gravitational pull is impossible. You might be wondering, why all this fuss about information? Why are we so concerned about whether information is lost in black holes, while we seem less bothered about the matter that falls in? After all, matter is also a fundamental component of the universe, isn't it? Well, it turns out that information and matter are deeply intertwined in the quantum world. In fact, in many ways, information is more fundamental than matter itself. Think of it like this: matter can be created and destroyed. For example, in nuclear reactions, matter is converted into energy, and vice versa. But information, according to the laws of physics as we currently understand them, cannot be created or destroyed. It can only be transformed. This fundamental difference between matter and information stems from the principles of quantum mechanics. In quantum mechanics, the state of a system is described by its wave function, which contains all the information about the system. The evolution of the wave function is governed by the Schrödinger equation, which ensures that information is always conserved. So, while matter can change forms and even be annihilated, the information that describes it must always be preserved. This is why physicists are so concerned about the black hole information paradox. If information is truly lost in black holes, it would violate one of the most fundamental principles of quantum mechanics, with far-reaching implications for our understanding of the universe. So, where does the paradox come in? Well, it all boils down to one of the most fundamental principles in physics, the conservation of information. This principle states that, just like energy, information cannot be created or destroyed, only transformed. It's a cornerstone of our understanding of how the universe works, underpinning everything from the laws of thermodynamics to the behavior of quantum particles. To understand this better, let's consider a simple example. Imagine you burn a piece of paper. The paper turns to ash, but the information contained in the paper, the words, the images, isn't truly destroyed. It's transformed into other forms, such as the smoke and the heat released during the burning process. In principle, if we could carefully track all the particles and energy involved, we could reconstruct the information contained in the original paper. This principle of information conservation is deeply ingrained in quantum mechanics, the theory that governs the microscopic world of atoms and particles. In quantum mechanics, the evolution of a system is described by a mathematical object called the wave function, which contains all the information about the system's state. The laws of quantum mechanics ensure that the wave function evolves in a way that preserves information. However, black holes seem to throw a wrench into this neat picture. According to Einstein's theory of general relativity, anything that falls into a black hole is inevitably crushed into the singularity, its information seemingly lost forever. This apparent violation of information conservation is what gives rise to the black hole information paradox. The paradox becomes even more perplexing when we consider Hawking radiation. In the 1970s, Stephen Hawking made the groundbreaking discovery that black holes aren't entirely black. Due to quantum effects near the event horizon, they emit a faint stream of particles, known as Hawking radiation. Hawking initially argued that this radiation is completely random and carries no information about the matter that fell into the black hole. If this were true, it would imply that information is indeed lost when objects fall into black holes, leading to a fundamental conflict between general relativity and quantum mechanics. This conundrum has spurred physicists to explore a plethora of potential solutions, each more mind-boggling than the last. Some researchers suggest that information might be subtly encoded in the Hawking radiation after all, perhaps in the correlations between the emitted particles. Others propose that the information might be preserved in some unknown form within the black hole, possibly at the singularity or even on the event horizon itself. One particularly intriguing idea is the holographic principle, which suggests that the information about the interior of a black hole might be encoded on its surface, much like a hologram stores three-dimensional information on a two-dimensional surface. This principle has profound implications for our understanding of space, time, and gravity, suggesting that the universe might be fundamentally holographic in nature. And then there are those truly out there solutions, the ones that really make you question the fabric of reality. We're talking about the possibility of information escaping black holes through wormholes or even baby universes. Now, wormholes, as you might know, are hypothetical tunnels that connect different points in space-time. Think of them as cosmic shortcuts, potentially allowing matter and information to travel vast distances instantaneously. Some physicists have theorized that wormholes could form inside black holes, providing a conduit for information to escape to another region of space-time, or perhaps even another universe entirely. Imagine all the information that falls into a black hole isn't destroyed, but instead gets shunted through a cosmic backdoor to a whole new reality. It's a mind-blowing concept, and while there's no direct evidence for it yet, it's a possibility that some physicists are actively exploring. And then there's the idea of baby universes. This concept proposes that new universes could be born inside black holes, budding off like branches from a tree. These baby universes would carry with them the information that fell into the black hole, preserving it in a new and separate reality. Think of it like this: our own universe might have been born from a black hole in another universe. It's a dizzying thought, and it raises all sorts of questions about the nature of reality and the multiverse. Of course, both wormholes and baby universes are highly speculative concepts. We don't have any definitive proof that they exist, let alone that they play a role in resolving the information paradox. But the fact that physicists are seriously considering these possibilities shows just how far they're willing to go to solve this cosmic puzzle. But the plot thickens further yet. The black hole information paradox isn't just an isolated puzzle, it's deeply intertwined with some of the biggest unsolved mysteries in the universe. It's like a cosmic web, with threads connecting it to questions about dark matter, dark energy, the origin of the universe, and even the existence of the multiverse. Let's start with dark matter and dark energy. These mysterious entities make up the vast majority of the universe, yet we know very little about them. Dark matter doesn't interact with light or ordinary matter, but its gravitational influence is evident in the motions of galaxies and clusters of galaxies. Dark energy, on the other hand, is a repulsive force that's causing the expansion of the universe to accelerate. Now, some physicists believe that black holes might play a role in the dark matter and dark energy puzzles. For example, primordial black holes, hypothetical black holes that formed in the early universe, could potentially account for some or all of the dark matter. And some theories suggest that dark energy might be related to the properties of black holes, particularly their ability to warp space-time. Then, there's the Big Bang, the explosive event that marked the beginning of our universe. The conditions at the Big Bang were incredibly extreme, similar to those found inside black holes. By studying black holes, we might gain insights into the very first moments of the universe, and the processes that led to the formation of galaxies, stars, and planets. And speaking of the Big Bang, some theories suggest that our universe might not be the only one. The multiverse hypothesis proposes that there could be countless other universes, each with its own set of physical laws and constants. And guess what? Black holes might be the key to accessing these other universes. As we discussed earlier, some physicists believe that black holes could be connected to other universes through wormholes, or even give birth to new universes. If this is true, then studying black holes could provide us with a glimpse into the vast multiverse and its infinite possibilities. Okay, now let's get philosophical for a moment. The black hole information paradox isn't just about physics and equations. It challenges our very understanding of reality itself. It forces us to confront some deep questions about the nature of cause and effect, the flow of time, and the predictability of the universe. See, one of the core tenets of classical physics is determinism. This is the idea that if you know the initial conditions of a system, the position and momentum of all its particles, for example, you can, in principle, predict its future behavior with perfect accuracy. The universe, in this view, is like a giant clockwork mechanism, ticking along in a predictable and predetermined way. But the information paradox throws a wrench into this neat picture. If information is truly lost in black holes, then the universe loses its predictability. The past wouldn't necessarily determine the future, and the universe would become fundamentally uncertain. Imagine this: two identical objects fall into a black hole. According to classical physics, their fates should be identical, but if information is lost, there's no way to tell what happens to them inside the black hole. They could be destroyed, they could emerge in another universe, or they could undergo some other unknown transformation. The point is, their future becomes unpredictable. This loss of predictability has profound implications for our understanding of reality. It suggests that the universe might be more chaotic and less deterministic than we previously thought. It also raises questions about the nature of time. If the future is not entirely determined by the past, does that mean time flows in a more complex way than we perceive? Some physicists have even suggested that the information paradox might be connected to the arrow of time, the seemingly irreversible direction of time from past to future. If information is lost in black holes, it could disrupt the smooth flow of time, creating ripples and eddies in the fabric of space-time. These are deep and complex questions, and we don't have all the answers yet. But the black hole information paradox forces us to confront these questions and rethink our assumptions about the nature of reality. It's a reminder that the universe is full of surprises and that our understanding of it is constantly evolving. This next idea is pretty out there. It's called black hole complementarity, and it's a truly bizarre concept that suggests information is both preserved and lost in a black hole, depending on your point of view. How is that even possible, you ask? Well, it all comes down to the strange and wonderful world of relativity. Einstein's theory of relativity tells us that time and space are relative, meaning they can be experienced differently by different observers. So, imagine two observers, one safely outside the black hole, watching an object fall in, and another unfortunate soul who's actually falling into the black hole. From the outside observer's perspective, the object never actually crosses the event horizon. Instead, it appears to slow down as it approaches the event horizon, eventually freezing in time and becoming increasingly redshifted until it fades from view. The information about the object, however, is preserved on the surface of the event horizon, encoded in the subtle distortions of space-time. But from the perspective of the infalling observer, things are quite different. They would cross the event horizon without noticing anything unusual, eventually reaching the singularity and being crushed out of existence. From their point of view, the information is indeed lost. So, who's right? Is the information preserved or destroyed? Well, according to black hole complementarity, both observers are right. The paradox is resolved by the fact that the two observers can never compare notes. The infalling observer can't send a message back out of the black hole to tell the outside observer what they saw, and the outside observer can never see what happens to the infalling observer beyond the event horizon. It's a mind-bending concept, but it's one way that physicists are trying to reconcile the conflicting predictions of general relativity and quantum mechanics. Black hole complementarity suggests that there's not necessarily a single true reality, but rather different perspectives on reality, depending on the observer's frame of reference. Now get ready for a truly fiery concept, black hole firewalls. This idea throws a bit of a curveball into our understanding of black holes, suggesting that the event horizon might not be the smooth, empty boundary we once thought it was. Instead, it might be a seething inferno, a region of intense energy that would incinerate anything that dares to cross it. This idea arose from attempts to resolve the information paradox while preserving the basic principles of both general relativity and quantum mechanics. However, it leads to a rather dramatic consequence. Remember the equivalence principle we talked about earlier. It states that an observer freely falling into a black hole shouldn't experience anything out of the ordinary at the event horizon. It should be a smooth transition, like floating through space. But if firewalls exist, that peaceful journey takes a fiery turn. Instead of a gentle glide across the event horizon, the infalling observer would encounter a wall of intense energy, instantly vaporizing them. Not a very pleasant experience. This dramatic scenario seems to contradict the equivalence principle, which is a cornerstone of general relativity. So, how can firewalls be reconciled with our current understanding of gravity? That's a question that physicists are still grappling with. However, firewalls do offer a potential solution to the information paradox. If the event horizon is a blazing inferno, it could prevent information from ever entering the black hole in the first place. The information would be effectively scrambled and radiated away as heat before it could cross the event horizon. Of course, the firewall idea is still highly controversial. Many physicists find it difficult to accept that the event horizon, which seems so benign from the outside, could be such a violent and destructive place. But the firewall paradox, as it's sometimes called, has forced physicists to re-examine their assumptions about black holes and the nature of space-time. It has also sparked a lively debate about the fundamental principles of physics. Does the equivalence principle always hold true, even in the extreme environment of a black hole? Or do quantum effects near the event horizon lead to unexpected and dramatic consequences? These are questions that physicists are still actively investigating, and the answers could have profound implications for our understanding of the universe. Now let's dive into a concept that's a bit more abstract, but equally mind-bending: gravitational decoherence. This idea explores the possibility that the intense gravitational field near a black hole could have a peculiar effect on quantum systems, causing them to lose their coherence. But what exactly is quantum coherence, you ask? Well, it's a fundamental property of quantum mechanics that allows particles to exist in multiple states simultaneously, a phenomenon known as superposition. These different states can interfere with each other, creating wave-like patterns of probability. Coherence is what allows quantum computers to perform calculations that are impossible for classical computers. It's also what gives rise to many of the strange and counterintuitive phenomena of the quantum world, such as entanglement and tunneling. However, coherence is a delicate property, easily disrupted by interactions with the environment. This process, known as decoherence, causes quantum systems to lose their quantumness and behave more like classical objects. Now, some physicists believe that the extreme gravitational field near a black hole could induce a particularly strong form of decoherence, scrambling information in a way that makes it practically irretrievable. It's like throwing a jigsaw puzzle into a blender. The pieces are still there, but they're so jumbled up that it's impossible to put them back together. This gravitational decoherence could potentially resolve the information paradox by explaining how information can be effectively lost, even if it's not technically destroyed. The information would still be present in the black hole, but it would be so thoroughly scrambled that it would be impossible to extract. Think of it like this. Imagine a library full of books. If you burn all the books, the information they contained is lost. But if you take all the books and randomly shuffle their pages, the information is still technically there, but it's become completely inaccessible. This idea of gravitational decoherence is still being explored, and there's no definitive proof that it's the correct solution to the information paradox. However, it offers a fascinating glimpse into the interplay between gravity and quantum mechanics, and it could have serious implications for our understanding of black holes and the nature of information itself. Alright, now prepare to have your mind truly blown. We've explored some wild ideas so far, but this one takes the cake. What if information itself is not fundamental? What if it's not a basic building block of reality, but rather an emergent property, something that arises from more fundamental entities or interactions? This is a radical concept, one that challenges our deepest assumptions about the universe. We tend to think of information as something essential, something that exists independently of the observer. But what if that's not the case? What if information is simply a way that we, as conscious observers, perceive and organize the universe? Think of it like this. A table is made of atoms, but tableness is not a property of individual atoms. It's an emergent property that arises from the way those atoms are arranged and interact. Similarly, information might not be a fundamental property of the universe, but rather an emergent property that arises from the complex interactions of more fundamental entities, perhaps at the quantum level. This idea has profound implications for the information paradox. If information is not fundamental, then the paradox might simply dissolve. The question of whether information is lost in black holes becomes meaningless if information is not a fundamental aspect of reality. This perspective also opens up exciting new avenues for research. If information is emergent, then what are the underlying entities or interactions that give rise to it? How does information emerge from the quantum world? And what does this tell us about the nature of consciousness and our place in the universe? These are deep and challenging questions, and we're only beginning to scratch the surface of this fascinating idea. But the possibility that information is not fundamental offers a radical new perspective on the information paradox and could lead to a profound shift in our understanding of the universe. Alright, let's switch gears and explore a concept borrowed from the cutting-edge world of quantum computing, quantum error correction. Now, you might be wondering, what does quantum computing have to do with black holes? Well, it turns out that both deal with the delicate nature of information and the challenges of preserving it in the face of noise and disruption. In quantum computing, information is encoded in fragile quantum states, which are prone to errors due to interactions with the environment. To protect this information, physicists have developed sophisticated error correction codes that can detect and correct these errors, ensuring that the information remains intact. These codes work by encoding the information in a redundant way, spreading it across multiple qubits, the quantum equivalent of bits. Even if some of the qubits are corrupted, the information can still be recovered from the remaining ones. Now, some physicists have proposed that similar error correction mechanisms might be at work in black holes. The idea is that the information that falls into a black hole is not simply lost, but rather encoded in a highly non-local way, spread across the entire event horizon or even the entire black hole interior. This black hole error correction code would be incredibly robust, capable of protecting the information from the extreme conditions near the singularity. Even if some of the information is scrambled or lost, the remaining information could be used to reconstruct the original data. This idea is still very speculative, but it offers a tantalizing possibility for resolving the information paradox. It suggests that black holes might not be the information destroyers we once thought they were, but rather sophisticated information processors, capable of storing and protecting vast amounts of data. It also raises some fascinating questions about the nature of information and computation. Could black holes be the ultimate quantum computers, capable of performing calculations that are impossible for any human-made device? Could they hold the key to unlocking the secrets of quantum gravity and the unification of physics? These are questions that physicists are actively exploring, and the answers could revolutionize our understanding of the universe and our place within it. Alright, now let's delve into one of the most bizarre and counterintuitive aspects of quantum mechanics non-locality. This concept, which Einstein famously called spooky action at a distance, challenges our classical notions of space and time, suggesting that objects can be connected in ways that defy our everyday intuition. At the heart of non-locality lies the phenomenon of quantum entanglement. When two particles are entangled, they become linked in such a way that their fates are intertwined, regardless of the distance between them. If you measure the properties of one particle, you instantly know the properties of the other, even if they're light years apart. This instantaneous connection seems to violate the principle of locality, which states that physical influences cannot travel faster than the speed of light. But countless experiments have confirmed the reality of entanglement, forcing us to rethink our understanding of space and time. Now, some physicists believe that non-locality could play a crucial role in resolving the black hole information paradox. The idea is that the information that falls into a black hole doesn't simply disappear, but rather becomes entangled with the Hawking radiation that escapes from the black hole. This entanglement would create a non-local connection between the information inside the black hole and the information in the Hawking radiation. Even though the information inside the black hole is inaccessible to us, it could still be preserved in the subtle correlations between the particles of Hawking radiation. Think of it like this. Imagine you have two gloves, one left and one right. You put one glove in a box and send it to a friend on the other side of the world. When your friend opens the box and sees the left glove, they instantly know that you have the right glove, even though you're thousands of miles apart. In a similar way, the information that falls into a black hole could be entangled with the Hawking radiation, creating a non-local connection that preserves the information, even though it's hidden behind the event horizon. This idea is still very much under development, and there are many challenges to overcome before we can say for sure whether non-locality plays a role in resolving the information paradox. However, it offers a fascinating glimpse into the interconnectedness of the universe and the potential for quantum mechanics to resolve some of the deepest mysteries of cosmology. So, as you can see, the black hole information paradox is not just a fascinating puzzle in its own right. It's a gateway to exploring some of the deepest and most profound questions about the nature of reality. By unraveling the mysteries of black holes, we might unlock the secrets of the universe itself. These ideas might sound like something straight out of science fiction, but they're based on cutting-edge theoretical physics and are being explored by some of the brightest minds in the field. And who knows, maybe one day we'll discover that the universe is even stranger and more wondrous than we ever imagined. The black hole information paradox isn't just a theoretical curiosity. It has profound implications for our understanding of the universe and our place within it. If information is truly lost in black holes, it would challenge our most basic assumptions about the nature of reality and the laws of physics. However, the quest to resolve this paradox has already led to remarkable breakthroughs in our understanding of black holes, quantum gravity, and the interconnectedness of space-time. It has spurred the development of new theoretical frameworks such as string theory and loop quantum gravity, which attempt to unify general relativity and quantum mechanics into a single, coherent theory. The black hole information paradox remains an open question, a tantalizing puzzle that continues to inspire and challenge physicists. But one thing is certain: the journey to unravel this cosmic mystery is leading us to a deeper and more profound understanding of the universe and its fundamental laws. Please, let me know what you think. Is information truly lost in black holes, or is there a hidden mechanism that preserves it? Let us know your thoughts in the comments below. And as always, thanks for joining us on this cosmic adventure. Don't forget to like and subscribe for more stellar stories. See you next time.